Hello everybody, this is Ruth Stuckey with part 2 of Module 7a. We have our usual copyright warning. Now when we're talking about radioactivity, the term nuclear radiation describes all forms of radiation that originates in the nucleus of the radioactive atom or the radionuclide. Some non-radioactive atoms can be converted to radioactive atoms when an extra neutron is captured by the nucleus. The radioactive nucleus is unstable because of the extra energy that the neutron has added to the nucleus. It gets rid of the excess energy and returns to a stable state by emitting subatomic particles and gamma rays from the nucleus. The most commonly encountered types of ionizing radiation are alpha, beta and neutron particles. Alpha particles are relatively slow and heavy compared with other forms of nuclear radiation. The particles travel at 5 to 7% of the speed of light, or 20 million meters per second, and have a mass approximately equivalent to 4 protons. These consist of a cluster of 2 protons and 2 neutrons, usually expelled by heavier elements such as uranium. Because of their high mass, alpha particles have a high probability of interacting with matter and therefore have a short range, which is usually a few centimeters in the air. Alpha particles are stopped by a piece of paper or the outermost layers of skin, and if the alpha-emitting material is kept outside the body, little damage results from these particles. Alpha emitters are hazardous when taken into the body and irradiate the body internally. Alpha emitters can be chemically similar to calcium in their action within the body and become part of the structure of the bone, remaining there for long periods of time. As they disintegrate, they emit alpha particles which can damage tissue. Beta particles consist of electrons which are ejected from the nucleus of unstable atoms. They are smaller and lighter than alpha particles, although they carry less energy, and they therefore can travel further in air, usually centimeters to meters. These particles can penetrate to tissue about 1 centimeter deep and can therefore give rise to significant skin doses. When higher energy beta particles are slowed down or stopped by heavier metals such as copper or lead, they produce secondary X radiation. Therefore, because of this secondary radiation, the lighter metals such as aluminium are used to shield beta sources, which are approximately, it takes approximately 1 centimeter of aluminium to shield. Like alpha particles, beta particles can be a significant internal radiation hazard. Neutrons have no overall charge and are released during the disintegration of heavier elements such as uranium, usually only within nuclear reactors, accelerators or other high-energy devices. In the human body, neutrons produce secondary radiation emissions, proton, gamma ray, beta or alpha particles, which are responsible for tissue damage. Gamma and X-rays are electromagnetic and ionizing radiations which have the same fundamental properties as lights and radio waves. Thus, gamma rays and X-rays control. The human body can tolerate a certain amount of exposure due to ionizing radiation without impairing its overall function. We're continually exposed to ionizing radiation from natural sources such as cosmic radiation from outer space and from radioactive materials in the Earth and materials around and within us. This background radiation is part of our normal environment. External radiation sources, or those sources that are located outside the body, present an entirely different set of risks to radionuclides or radioactive materials that have entered the body. Once inside of the body, the radionuclides have absorbed, metabolized, and distributed throughout the tissues and organs according to their chemical properties. Their effect on organs or tissues depends on the type and energy of the radiation and residence time within the body. The effects of a radiation on living systems are evidenced by the effect on living cells, the changes in the biomechanical reactions, the production of disease, or the changes in life or normal growth patterns. The effect of radiation on living tissue is generally assumed to be almost entirely due to the ionization process. Radiation strips electrons from their atoms and breaks their chemical bonds with other atoms. This can destroy the capacity of the reproduction or cell divisions in some cells or cause mutation. The outcomes of radiation have different injurious effects. With ionizing radiation, there's the somatic effects, injury to individuals, and genetic effects, which can be passed on to future generations. The degree of injury depends on such factors as the total dose and the rate at which the dose is received, the type of radiation, and the body part receiving it. In general, if the total amount of radiation is received slowly over a long period of time, a larger dose is required to produce the same degree of damage than if the same total dose is received over a short period of time. The time between the exposure and the first sign of damage is called the latent period. The larger the dose, the shorter the latent period. The various tissues and organs of the body are not affected equally by equal radiation. For example, tissues such as bone marrow, which contains blood-forming cells, the lining of the digestive tract, and some cells of the skin are more sensitive to radiation than those of the bone, muscle, and nerve. The same dose of different forms of radiation may have different effects due to the different characteristics of these forms of radiation, as already discussed. The equivalent dose, which is expected in sieverts, or millisieverts we hope, is used as a measure of biological damage. The acute toxic effects from radiation exposure include weight loss. This chart has a very small number of radioactive substances listed, but it gives you some examples which show the type of radiation emitted, the half-life of the material, the biological half-life, and the main target organ in the body. You can get these lists really easily, and if anyone wants more information on them, I'm very happy to provide them. They're also on the APANSA website. But as you can see, different radionuclides have different target organs, and a range of ionizing radiation is used in industry and the medical sector. We've talked already about some of the industrial uses, and they're listed here. Ionizing radiation is also encountered in research units such as universities, uranium mines, and reactor installations. In all of these places, they are tightly regulated with tight standards, and they should be regularly, and all of them. There's been extensive work done in an attempt to relate radiation dose to resulting damage. Studies have been carried out of the survivors of the nuclear bombs dropped on Japan, of medical and accidental radiation exposures, and of exposures to radium and X-rays during the first quarter of the last century, and from laboratory experiments with animals. Using these studies as the basis, dose standards or limits have been set at a level where the calculated radiation risk is no more than that due to other risks already accepted by society. The philosophy behind the dose limits is to provide protection to the individual, their progeny, immediate generation and those after, and the population as a whole. And you can see a series of sources of exposure here, and what the when we're looking at measurement of ionizing radiation, we need to be aware that the human body is unable to detect ionizing radiation at all through any of its senses. It's, however, the biological damaging aspect of the radiation, or its ionizing properties, that enables instruments to detect and measure it. There's two main types of radiation detectors: simple detectors and dosimetry instruments. The simple detectors are mainly used for detection of detection of exposure and contamination monitoring. These are generally capable of detecting very small amounts of radiation. They don't give a uniform response for different radiation energy levels, but they're only accurate for the type of radiation for which it's calibrated. Dosimetry instruments are used for personal monitoring, and the common one is the thermoluminescent dosimeter, which is known as usually the TLD, which is much more easy to say. And these are usually badges, film badges, and pocket dosimeters. The TLD and film badges are worn by the worker, and after a period of time or after a suspected exposure are sent to a radiation laboratory for determination of the amount of radiation energy which has been absorbed. The pocket dosimeter is a direct reading portable unit shaped like a pen with a pocket clip. The main advantage of these pocket dosimeters: radioactive sources may enter the body by absorption through the skin, by ingestion, including hand-to-mouth transfer, or by inhalation. Alpha and beta radiation in particular presents an internal radiation hazard. Unlike exposure to external sources, which cease when the person leaves the radiation area, radioisotypes in the body continue to irradiate after leaving the area where contamination has occurred. Thus, their hazard is more difficult to assess, and a greater emphasis therefore given to the prevention of internal contamination. The key factors in control may be summarised as containment, cleanliness, and cut. To prevent radioactive material entering the body, the following general rules should be applied: provision of proper and adequate containment for unsealed sources, the regular maintenance and monitoring for contamination, the use of suitable PPE, decontamination immediately after spillages, maintenance of good housekeeping, no smoking, eating, drinking, or using cosmetics or pipettes by mouth in potentially contaminated areas, and checking of yourself for personal contamination on leaving a potentially contaminated area. Ionizing radiation exposure limits are set by the International Commission on Radiological Protection, the ICRP, and the contamination for general public exposure should be not more than 1 millisieverts over a year, and that's over and above the natural background. That's particularly important for people like visitors at radiation units in hospital who've accompanied people who are being treated with ionizing radiation. The occupational exposure is set at 20 millisieverts per annum, and that's an averaged over 5 years with no more than a dose of 50 in one of those years. And again, those limits exclude exposure due to background and medical radiation. We measure in millisieverts, and those people who are occupationally exposed to ionizing radiation should be monitored with the dosimeter worn as the badge or the TLD reader at monthly intervals. That's sent to a laboratory where the radiation exposure can be read. And in Australia, the average radiation worker receives a dose of 0.12 millisieverts per annum, which is well within the guidelines. What you have there is a picture of a number of these badges and measuring equipment, and what you also see is the rings that are used on fingers where just fingers are being exposed, particularly with the insertion of some of these materials into the practical control of radiation dose is dependent upon whether it poses an internal or external exposure, dose, and hazard. The external source exposures to external radiation can be controlled by the application of one or more 3 fundamental rules, and these are really important. These are time, and the less time spent being exposed to radiation, the smaller the dose. There is a direct relationship between exposure dose and duration of exposure. Reducing exposure time by 1/2 reduces the dose received by 1/2. And these are really important understandings in this area. The distance, increasing the distance from a source of radiation reduces the dose. As a rough approximation, the inverse law, square law, can be applied. This means that by doubling the distance from the source of radiation, the exposure would be decreased by 1/4 of the original amount. And again, that's a really important understanding. Placing a suitable absorbing material to provide shielding between the source and the person reduces the dose. The more mass that's placed between a source and a person, the less radiation the person will receive. The different types of ionizing radiation require different approaches to shielding. And if you ever go into an area where people are being given medical radiation doses, what you'll see, medical ionizing radiation doses, therefore external sources, what you'll see is that what they have is usually concrete mazes, because these doses can only travel in straight lines, but they can be reflected in straight lines off walls. So between the source and the person who's giving the dose, we have some references.